Image generation is quietly shifting from sample more and hope to systems that spend compute where it actually matters. One line of work makes diffusion MOE routers see cleaner structure instead of noisy latents, so expert capacity tracks salient regions more accurately. Another lets a masked discrete model revise its own earlier token choices and train stably with huge codebooks. The bigger trend is obvious: better quality and lower cost by making inference self-correcting. Keep watching, because the details here are exactly where the next generation of image models gets faster, sharper, and cheaper. Let's explore the first paper, focusing on what matters: saliency, harnessing accurate routing for diffusion MO, Sharp MO-E, developed by researchers from Huazhong University of Science and Technology and Alibaba Group's Tongyi Lab, targets a specific failure mode in diffusion mixture of experts models. Routers trained on noisy latents do not reliably allocate more experts to salient image tokens. The paper's core idea is to replace noisy routing with saliency-harnessed clean routing by feeding the router the previous step's predicted clean latent X0, which preserves structural and textural cues even at high noise time steps. SharpMO is implemented as a post-training, plug-and-play enhancement on pre-trained diffusion transformer backbones, including TCDT, ECDT, and diffmo, and is trained with a recursive full trajectory scheme over t equals 10 rollout steps. To explicitly align compute with visual importance, the authors add a trajectory routing loss that matches cumulative expert assignment to a Laplacian-based saliency map using KL divergence, with lambda routing equals 0.001. On ImageNet 256 times 256, after 100K post-training steps from 500K pre-trained models, SharpMO-E improves every evaluated backbone. For example, diffmo-L reaches FID 50, K 3.1, and IS 228.88 at CFG 1.5, while the baseline diffmo-L scores 3.86 and 203. Ablations show that saliency harnessing routing reduces diffmo-B FID 50K from 8.03 to 6.95 at CFG 1.5, and adding the trajectory routing loss further lowers it to 6.66, confirming that clean latent guidance and trajectory level compute regularization are both necessary for accurate saliency-aware expert allocation. Let's explore the third paper, Nemotron Labs Diffusion Image Advancing Masked Discrete Diffusion for High-Resolution Image Synthesis. NVIDIA's Nemotron Labs Diffusion Image advances masked discrete diffusion for 1024 pix text-to-image synthesis by fixing two core failures in standard MDMs: irreversible token commitments and sparse supervision from very large codebooks. The model uses an 8-bit decoder-only transformer initialized from Nemotron Labs Diffusion and a 131,072 code EMU3 5 tokenizer, then adds token editing, so already unmasked tokens can be revised during inference when confidence exceeds 0.6. To stabilize training with large vocabularies, it introduces grouped cross-entropy, which clusters discrete codes with k-means and adds hierarchical cross-entropy over 16,384 and 8,192 clusters, plus a fused custom operator that cuts GCE latency from 44.14 milliseconds to 20.04 milliseconds, and max VRAM from 25.2 gigabytes to 16.1 gigabytes, trained for 300K steps on 64 H100 GPUs over 16 days on 137 M text-image pairs. The system reaches 0.9 on GenEval, 85.2 on DPG, and 9,1 HPS-3 on MJHQ 3.0K. With additional synthetic fine-tuning, it rises to 86.9 DPG and 10.76 HPS-3. An ablation shows token editing makes 32 NFE sampling match, no edit, 64 NFE quality, effectively halving forward calls, and the full model is reported as 42.4 times faster than EMU3, 5 at comparable or better GenEval quality. That's a wrap on today's AI paper highlights. Thanks for watching.